Yeah. Hi, everyone. Thank you for joining. Today we're going to talk about exploring build caching, practical review. First thing first, who am I? My name is Martin Duhem. I've been a software engineer at Gradle for the past 2 years. I've been working on Develocity for SBT. Develocity is the build observability and acceleration platform that we work on at Gradle. Before that, I was working at Twitter. I was in the IDE, build, and developer experience teams. Before that, I was working on Scala Native, Bloop, Scala Free at the Scala Center, and even before that, I was working on Zinc and SBT at Lightbend. So throughout my career, I've been working one way or another on compilers and build tools. That's really one of my areas of interest. Today, we're going to first talk about what is build caching so that we can all get on the same page about what this is, what it's about, what are the benefits, and so on. We'll see what's available to us today, what we can do in SBT1X, and also discuss what it takes to deploy build caching in practice in an organization. So what is build caching? I think we can all agree that building takes too much time. And one of the reasons for that is that most of the time, the same work is being done over and over again. So we execute the same test, we build the same sources that our colleagues or CI machines already built, and so on. The idea of build caching is to reuse some of those results or the entirety of those results if nothing has changed. So to make it just a bit more concrete, we can imagine that the build is expressed as a collection of pure functions. In this example, we'd have one function called compile, takes as input the sources, the compiler options, a class path, produces a jar with the compiled class files. You can also imagine we have second one, test, it takes the test configuration, like do we fork, what reports do we have, and so on, and a class path to execute the tests again, would produce a test report. So we said that those functions are pure, so if we call them twice with exactly the same arguments, we should get exactly the same result. So we can imagine now that we define a function called hash, which we would pass a function, one of our build functions, and the arguments, produce a long, that would be based on what the function does. So having that, we can then associate the function call and its argument with a stable hash. For instance, if we call this hash function on the compile function, and we pass it empty sources, empty class paths, and no compiler arguments, we would get some hash. If we pass different source files, we get different hash, and so on. So having that, we can now imagine that we define a cache that we can pass cache keys to and expect a result back. So we define a subject cache that has get, given a key. It will try to retrieve some value t if it exists. We define also some helper method to make it easier to define cached functions, to which we can pass the function, the arguments that we would like to execute it against. It will try to retrieve the thing. If it finds it, then good. We can just return that result. If not, we evaluate the function, and we can update the cache. So that's it. That's the idea behind build caching. So we've seen it's simple, but why would we want to do that eventually? So if we have build cache, then we can have our local and CI builds reuse the previous results. And that's going to be faster, of course. Doing that, we can also avoid some work. So we consume less energy, we save some money. And because things go faster, we have happier and more productive engineers. But what's more interesting also is that once we have build caching, we can also enable other acceleration techniques. One example would be distributed builds, where instead of having, let's imagine you have a project with 10 modules and one root module that everyone depends on. You don't want to have all your CI machine to rebuild over and over the same root module. You can build it once, put it in the build cache, and then all the other worker nodes can just pull that from the cache and build what's depend on it. The same goes for test execution. You could compile the test just once and then distribute the results and run the test classes in parallel. So it looks good, but of course, it's not always that easy. The example that we've seen before, it's a bit simplified, and there are many things to consider if we want to really implement build caching. First, we had this hash function that we did not really describe. How do we implement hashing of a function? Also, we need to make sure that we have inputs and outputs to our functions that are completely machine independent. Because for instance, if you pass an absolute path to the compile function, for instance, your class path or to pass to your source files, then you're going to compute the cache key against that. And on a different machine, the path is most likely going to be different, leading to a different cache key, and then cache misses, where you would have wanted to have hits. You also need to make sure that the outputs that you produce from your build functions are stable. So that means that, for instance, if your output includes some timestamps or your username or something like this, if you run it on a different machine, it's going to be different. And then whoever depends on that is going to not get the bytes that they expect. Another example of thing that we need to pay a lot of attention to is that we want to capture all the inputs and outputs and the effects. Because, for instance, if you change the Scala compiler version, then you would expect that what you had built before with an older version should not be used anymore. But if you don't capture that compiler version in the inputs of your task, then it's going to be reused, and that's an issue. The same goes, for instance, for the effects of your task. If you write some file on disk somewhere, but your build cache is not aware of it, then if you then restore that task result from the cache and you don't rewrite this file on disk, it's going to be missing and it's going to be an issue for the rest of the build. So there are many things that we need to pay attention to. It's not easy, especially when you are running in an uncontrolled environment. I think most Scala engineers are also familiar with the concept of incremental compilation. So just to draw an aside, we can also say that incremental compilation is some form of build caching. If you're familiar with Zinc, you may know that it takes the symbols that are defined in your source files and build a graph of it. The symbols that are defined, like the classes, the values, the method that you define, are the nodes of this graph, and the dependencies between those are the edges. When you change your source file, Zinc is going to recompile it and see what symbols have changed. If a symbol has changed, then it's going to look at the ones that depend on it and recompile those as well. And if nothing has changed, then it can just reuse this previous result. So that's a form of build caching as well. So let's take a look quickly at what we have today available in the industry for build caching. One well-known example of build caching is the one implemented by Bazel, which has built-in and automated support for build caching. One of the reasons why caching is so effective with Bazel is that it is artifact-based. So if you've seen a Bazel build, you have those different build steps which typically consume artifacts and produce more artifacts, so files on disk. And the dependencies between those artifacts are very explicitly tracked in the build files. Moreover, if you've seen all those what we call rules, which are kind of those functions that you can see in build files from Bazel, in their implementation, it's done in a way that Bazel is automatically aware of the side effects that are produced by the rules. Also, the inputs and the outputs are explicitly declared. So as a result of that, because of those constraints, you have that the build caching should work out of the box in most cases. Of course, in practice, there are details that make it sometimes a bit harder, but it should work out of the box, at least that's the theory. In SBT1X, we do not have this, because SBT is task-based. And a task, it can do basically anything that you could do on the JVM. You can consume anything, you can depend on other tasks, which can produce any arbitrary result. But at least we have the dependencies between those tasks that are encoded in the SBT task graph. Because we don't have that much control over what happens, we can't have really generalized automatic build caching in SBT1X. However, SBT still has some specialized caching where it makes sense. In SBT2, the situation is going to be better because there is the implementation for remote and local cache. There is a proposal and an implementation of generalized build cache for SBT2 that I'm sure Eugene is going to mention tomorrow. It includes both a disk cache local to the machine and a remote cache which uses the Bazel caching protocol. So meaning that you can deploy a Bazel compatible build cache in your infrastructure and just connect SBT to it, which should be able to use it. By default in SBT2, I believe all tasks will be cached, but there are a few things that you need to pay attention to in the implementation of your task. Whenever you want to produce some output, you have to declare it. We declare output, and SBT is going to be able to take care of the rest. So we've seen a bit of the landscape, but what can we do now in SBT1X? Because it's still the one that's released at the moment. So we mentioned that SBT has some specialized support for the caching of certain tasks. One of those is called cached resolution, which is local to the machine. It's used to cache the subgraphs that are resolved when doing dependency resolution with update. It's used to speed up dependency resolution. Another example is incremental compilation that we briefly mentioned before, and also cached compilation, which is remote. We will discuss it a bit more soon. But also, and maybe less well known, there are a few APIs that exist in SBT that you can use to implement a local or remote or any kind of cache that you want. The first example is cache.cache, which can be used to reuse consecutive results of a given function that uses the same argument. File function.cached is the same, but it operates on a set of 5 to a set of 5. Then you can also track differences in input, in output, and there is .previous that you can call on task to get the result that was produced before, and so on. SBT has quite a few APIs to do caching. So we mentioned briefly remote compilation caching. So this is something that's supported out of the box in SBT1. I think it's been there for quite a while, so it's very likely that your build should be compatible today. The way it works is that you take the class files and the incremental compiler state, and you push that to a remote cache. There are a few tasks that are involved in doing this. One of those is push remote cache, which surprisingly pushes to the remote cache, takes the class files, the compiler states, creates an archive, put it in the remote cache. Pull remote cache does the reverse. It just pulls from the cache, restores the incremental compiler state, and so on. A remote cache ID is the one that is used to create the cache key that we discussed before. But the feature, while it works, it's not super user-friendly because you need to remember to use it. But the idea behind it is that in the morning, you open your laptop, you would get the latest changes from main, you pull from the remote cache, it restores the incremental compiler state, and then you're ready to work. On the other hand, you would also have your CI machines. Whenever something gets merged to main, they would do the compilation, run the test, and so on, and then push the remote cache so that it's available to anyone. So that works, but still it requires some work. You have to remember to use it, and so on. So how can we make it easier to use? So the idea is that we could redefine the compile task so that it depends on pull remote cache. So yeah, sounds good. Let's try to implement it that way. So redefine compile, calling equal, compile depends on pull remote cache.value. That works well. Whenever we execute compile, because it depends on pull remote cache, it's going to do it. Pull remote cache, restore the incremental compiler state, and then try to compile, which should be hopefully a no-op. Good. So now we would also like to keep the remote cache up to date. So let's say that a push remote cache should be triggered by compile, so that whenever we execute compile, it's going to update the remote cache. Well, that's a good idea, but unfortunately, it doesn't quite work for two reasons. First, it would attempt to push to the remote cache even after a compilation failure, which is not something that we want. And it would also attempt to override the cache content after an op, which is wasteful. So we need a way to verify that the cache is already up to date. How can we do that? So the idea is that we would try to remember what was the last time that we pushed, what was the last time that we compiled, and if we pushed more recently than or at least as recently as the last compilation, then there is nothing to do. Otherwise, we push the remote cache and record that timestamp. And the whole thing is triggered by compile. So this is pseudocode. What would it look like in a real implementation? It's not too bad. So we can use previous that we discussed before to get the previous value of the same task execution, if we have one. If not, then just return some random value. We get the last compilation. So to do that, you have to know a few of the SBT APIs. So we get the compilation, compile, what value is going to give us the analysis from the compiler, from which we can get the compilations that happened, and the most recent one would be the last. We get the start time, and we have the time of the last compilation. If the last push is as recent, there is nothing to do. We can just keep the same timestamp for last push. Otherwise, we just push the remote cache and record that the last compilation is the time that we pushed for last time. And we just have to turn the whole thing to a dynamic task because we are going to execute the task or another depending on some condition. And eventually, the whole thing is just triggered by compile. So that works. Good. So it makes for something that is a bit more economic. So what we've seen here is based exactly on the same principles that we discussed at first. First, we have to gather everything that matters for the compilation. So those are the inputs of our task. Then we can compute a unique identifier, the cache key, and ask the remote cache for the value that is associated with this and restore it if it exists. In SBT's implementation of remote caching, the cache key takes into account the sources, the class path, and a few more options of the compiler, internal options, to create this key. It's a bit coarse, meaning that you will see more cache hits than you should, but it doesn't really matter in practice for SBT because we are going to invoke zinc afterwards, and if something needs to be recompiled, zinc will detect it and do it. But you can still, if you want, to configure a finer-grained cache key by overriding the remote cache ID task. So let's look at a different example now, how we can turn a plain task into a cache task. So let's say, for instance, that you want to make sure you don't depend on any GPL licensed code in your code base. So you would like to define something that's going to check on the licenses that you have in your dependencies. You will want to depend on that whenever you execute the test so that you're sure that it's going to be called by CI. To collect the licenses, you just look at the class path, you extract the license file from all the jars, and then you read those licenses. And if you find a GPL, you just raise an error. So it looks good, that would work, but whenever you execute the test, you're going to spend quite some time extracting all the jars, which can take some time if you have many of those. How can we improve so that if the class path hasn't changed, we don't have to do it again? So we can use the function that we've seen before. In this case, we use the file function that cached. If you remember, it was working on a set of file to a set of file, and we wrap the work that we want to do in that. So we have the inputs, which are going to be checked by SBT. We loop over those jars that are in the external dependency class path. We extract the license from the jars, and that's it. That gives us a new function that is cached, and we can just invoke it on the class path. The rest doesn't have to change, and now whenever you execute it, as long as the class path hasn't changed and the directory where you extract the jars hasn't changed, you won't have to redo the extraction ever again. So we can apply this technique to many common tasks in SBT. For instance, that would work for sources and resource generations, which most likely you don't have to regenerate on every compile. We can do it for verification, like we've just seen. You could do it for archiving, for instance, if you're building an Uber jar, or for shading, for instance, if your input jars haven't changed, why would you need to reshade them? Those APIs, they take as input a cache store. The cache store is an interface that is used to describe how the files are stored. So it will configure, you could define a cache store that works remotely, you can define a cache store that works on disk, or that synchronizes between the two, and so on and so forth. But still, even with those abstractions, you still need some knowledge about the implementation of the task so that you know how to change it. You still need to know which task you want to work on, because some of those may not be worth caching, and that's something that you need to identify. So let's look at a different example now. For instance, if we wanted to cache the test execution results. So if we go back to our first principles, what would it take to cache the test execution results? First, we need to compute a cache key, and for that we need to figure out what are the dependencies of the task. So if you're familiar with SBT, you most likely have read quite a few times the defaults.scala, which is basically the source of truth for SBT, and you can find here all the dependencies of the test execution. All right, so we have the dependencies of the task. We can use those to compute a cache key. So we can define the test parameters, which are basically the values that we've seen before, and then we define the execute test task, which is the one in charge of executing the test in SBT. So we keep the actual task, the one that does the work. We can do this by giving the key, execute test.task value, so that we get the work of the task. We compute the cache key, instantiate the store, where we're going to write our cache, which takes the cache key produces the test output, ask the cache for the cache key that we just defined. And in case of a hit, we can simply return that result. In case of a miss, then we have an update function to put the new value in the cache. We can execute the test, and then with the result, we update the cache and return the result. Looks simple enough, but can we generalize now? Because actually there's nothing that looks so specific to testing in what we've seen. So we've seen how we can collect the task input. It would be nice if we could do it automatically. So let's try to define this cache task. So a cache task, it would wrap a task that produces some value of type T. Here we need to say that this type T conforms to JSON format, because in SBT that's the type that you would use to serialize a value to JSON and be able to recreate it back from its JSON representation. We take as input the key that we want to cache, and we can again get the actual task that does the work. How do we compute the cache key is still a mystery. We instantiate the store, the cache, and given that cache key to the store, we can again try to update, try to get the value from the cache. If we have it, we just return it or update the task. Update the cache, sorry. So, since SBT encodes the dependency in the task graph, we can try to look at it and infer what are the dependencies. When we have dynamic tasks, however, it's not possible to compute the dependencies ahead of time because those depends really on what happened at runtime. But if we're working with non-dynamic tasks, we can just ask the build structure for those dependencies. Having those dependencies, we know what task to look for to gather the values that were produced and the values that are going to impact the evaluation of the task we want to cache. So how do we get this value? We can use in SBT something called the task progress, which is a listener which will get callbacks whenever there is some activity in the task engine. For instance, when a task has finished, if that's one of the tasks that we wanted to track, we can just get back its result and record it so that we can hash it later. So having all the outputs, we can compute finally some cache key. And that cache key can then be reused to try to retrieve the view from the cache if it's there. If not, we can evaluate the task and cache the result. So that's the theory, but still in practice there are a few more questions. So how do we hash the values? How do we take an arbitrary value that the task can create and create a cache key out of those? How do we account for the task implementation as well? And finally, how do you serialize any arbitrary result that the task can produce? So let's see now what it takes to actually deploy build caching in practice in an organization. So we've talked only about the technical details of implementing build caching. That's one part of the story, but it's not everything. If you really want to deploy build caching in an organization, we'll have to convince both management and developers that it's worth it. Because management's going to pay for the build caching, for time to implement it, deploy it, and so on. So to convince them, you can look at the return on investment. If you say that per build, you save that much time, you do that many builds per day, you have that many developers, each of them costs that much on average, you get some number, maybe it's worth implementing build caching or not. That could be convincing for management. Developers, on the other hand, they need some more numbers. They would like to know what are hit and miss rates that the build cache introduces. They want to know how much overhead they get by introducing the cache, because you need to compute cache keys, you need to interact with the cache and so on. That has a cost. They will want to know how much time was saved by introducing the cache. And finally, they need to understand how to spot stability issues. So to solve those, what you need is something that we call build cache observability. The idea is to emit events whenever some caching activity occurs. If you query your cache, you want to know if there was a hit or a miss so that you can record that. Along with that, you will also most likely want to know what was the task that queried the cache, with what outcome. What was the cache key that we used? If you have two builds and one resulted in a cache hit and the other in a cache miss, you want to know why the cache key was different between the two. Or if you retrieve something from the cache, you want to know how big it was. If you upload something to the cache, you also want to know how big it was, how many entries were in the archive. If you are downloading, most likely also you want to know where was the engineer so that you can better organize the network, and so on and so forth. So that's many reasons why you would want to get build cache observability. But there is also a very important reason, and that's eventually when the unavoidable happens, that is when you break the cache, you will need build cache observability to understand why it happens. So can you spot why this task, for instance, cannot be cached as it is right now? So the idea is to package the sources that you have. You take your compilation sources and just create a zip with those files in it. If you put that in the cache, unfortunately, it's not quite going to work. Can you tell why? The problem here, Eugene?
The side effect of the file is not really captured, so it's going to just return the file name. And also there's a capturing the file absolute path, right?
Mm-hmm. Plus also the zip is going to encode the timestamp and the last modification time. So it's going to change every time. Yeah, a different example now with source generation. You have a list of environment and you would like to generate some source that describe those environments. But unfortunately, if you try to put that in the cache again, you're going to run into some issues. Any idea why?
Environment isn't deterministic.
Exactly, yeah. So the source is not going to be the same each time you regenerate it. So you could think that, all right, those were issues in the build. I'm not a build engineer. Why would I care? All this one is not. This could be just the code that you build. It's basically the same issue, where you have a map with the list of, with the environments. And again, the expansion of this macro is not going to be the same all the time because of the set whose ordering is not deterministic. So you get class files that are not deterministic. And again, that's going to break the cache. So it's quite hard to prevent those from happening, but once you do, once that happens, it's really nice to have some observability so that you can detect those issues and understand where to look for. So to conclude, SPT1X already has a variety of functions that you can use to implement build caching in your build today. They can work with a remote cache. You can also make it work only locally. It really depends on what implementation you want to use. But unfortunately, if you want to cache arbitrary tasks, you need knowledge about the task implementation, and you need to be able to identify what are the parts that really need to be cached. When you implement build caching, you can greatly accelerate the build. The performance improvements that you can get are basically endless. If you have tests that take 2 days to execute, you can save those 2 days. But yeah, it's still quite a bit of work, and you need observability if you want to do anything more than small-scale build cache deployment. So that's what I had. Thank you very much. Have any questions?
Is it limited only to Scala source code or anything which is built by SPT, considering we don't have side effects like with zip file?
No, you could do it really with anything that you build. The remote cache, for instance, would work with Java sources and Scala sources.
Is there like a repository of like examples for this? I tried to play around with this a while ago and I couldn't figure it out, frankly. Do you have something available we can just take a look at and see how this is done for an open source project, or just an example maybe from you guys?
I do not. I remember that at some point we were looking into the performance of the Pekko build, and we identified with the observability platform that we have that there was one task that was taking a very long time to execute, which was being rerun over and over again. I believe we wrote at some point, it was linked in a blog post, I believe, in our website. I could try to find it again. But no, I don't have anything in particular.
So if there are no more questions, then if you think of something later, you can catch up with Martin. And thanks again for the talk.
Yep. Thank you very much. Oh yeah, and also we recently also deployed build caching in the Scala free build. We have some observability. So if you were interested, maybe come to the booth, the Gradle booth that we have. Tomorrow morning we'll also have some breakfast if you want. So I can talk build caching with croissant. It's going to be nice.